Hello everyone, welcome to third lecture of week 3 of the course Simulation of Modern Power Systems, in which we will continue the discussion on power flow analysis and will learn a very commonly used important power flow technique known as DC power flow. The importance of DC power flow comes from the fact that for network operators, system operators, if they have to understand, analyze the quick assessment for a given network disturbance, such as outage of a transmission line, outage of a generator, or sudden increase in the load, sudden change in the generation profile, then what would be the first immediate impact on the network in terms of real power flows, voltage phase angles, is where the DC power flow tool or technique comes in. It is not an exact or an accurate technique like fast decoupled power flow, Newton-Raphson power flow, or Gauss-Seidel method. It is a very approximate technique. It's a linear technique, which is where the term DC comes in. For typical circuits or DC circuits, when the sources are mentioned in terms of voltage sources or current sources, then the corresponding circuit equations that are involved for solving that DC circuit or circuits with known voltage and current sources, they tend to be all linear simultaneous equations, and there is no recursion or iteration involved. And that is where the technique or the method can be solved in just one go with no initial choice required also. The same thing happens in such a technique, and that is what is giving its name as DC power flow. The importance of which is to have quick assessment of network changes in terms of change in real power flows and voltage phase angles. The change in voltage phase angles and real power flows are not accurate numbers, but they give a trend of how the network disturbance is going to affect the system. The last discussion was on fast decoupled method, and the DC power flow technique draws its inspiration from this technique, fast decoupled method. So, what is the inspiration? What is the correlation or similarity? The principles which ALSA and Stott mentioned for fast decoupled method, in which they were able to decouple P theta half iteration and QV half iteration equations based on the assumptions that voltage phase angles differences are not very high for a well operating transmission network, and other such cases, the same implications would be true for the DC model of the network also. So, as I mentioned, this model of the network, power network, is not an accurate model, it is an approximate model, but it is widely used by system operators to get a quick assessment of the change that would, the impact that the network would have in case of sudden load changes, generation changes, or outages. So, this method or model provides reasonably good voltage phase angles when the line flows are not very high, which would mean that the load is not very high. The voltage profile at every network or every bus in the network is sufficiently flat, which means that the voltage magnitudes are all close to 1 per unit, and transmission lines, they do have low R by X ratio. So, for systems networks with highly inductive aspects, the corresponding DC model is able to provide good voltage phase angle estimates. Now, before I go deep, since DC model of the network or DC power flow or DCPF will be able to give voltage phase angles for all buses, then does it mean that the index I here would run from 1 to all the way till capital N? No. Here also we would require one bus to be acting as the angle reference bus. The reason for this would become evident in the next few slides. Please have patience. And hence, when the angle reference bus, whose angle we typically prefer to be choosing 0 radians or 0 degrees, we will stick to the 0 radian part. Radian is the by default engineering, electrical engineering convention for finding voltage phasors or other phasor quantities. Degrees, there could be mistakes involved. For every degree, when you put those degree values into the corresponding expressions, you have to be careful in settings of your calculators or your numeric platform, where every radian to degree conversion requires a factor of 180 by pi or pi by 180, depending on whether we are converting the radian value to degree or degree to radian respectively. So I would prefer using the reference for or the unit of angle to be radian. So angle reference bus phase angle is known, and hence index I runs from 2 to n, where we are trying to get these voltage phase angles from DC power flow. Since all voltage phase angles are to be obtained in DC power flow, that means there is absolutely no need to know what are my PV and PQ buses. The PV and PQ bus information is important from the perspective of voltage magnitude. DC model of the network, power network, assumes that voltage magnitudes are close to 1 per unit, which is true for lightly loaded systems, and hence in DC power flow we will never ever require the information of PV or PQ buses in DC power flow. So going ahead with the assumptions that were true for fast decoupled power flow, all elements that don't affect P theta iteration, that is line charging susceptance, line resistance, bus shunts, voltage regulators, they are not to be considered at all. These elements may be present in the power network, but while we solve DC power flow, we would consider these values to be 0. That is what the neglect term means. We will consider only phase shifters and line series reactances which affect the P theta half iteration. The difference of voltage phase angles is very, very small. So sine terms of the arguments can be replaced by the argument itself, and cosine is close to 1. Network has infinite reactive power capacity, which is where the concept of constant voltage profiles being sufficiently flat comes in, which leads to voltage phase magnitudes of all buses being equal to 1 pu, and that is also a reason why PV PQ information is not relevant in DC model. As a result of which, as I mentioned, voltage at every bus is 1 pu. Using these assumptions, if we now focus on the expressions of real power injection equations, then this is our actual expression of real power injection at bus I. Since cosine of one angle is 1, real power conductances are 0, only we have the B term where this phase angle sine is being replaced by the phase angle. So real power injection equation can be approximated by this form, which when expanded gives us two terms, one term for phase angle theta I itself and the other terms being for all other bus voltage phase angle, that is theta k, where k runs from 1 to n. BIK in this case is simply the inverse of the actual line reactance. If we define B0 matrix, above we have B matrix. In the bottom part, if we define B0 matrix where the elements are negatives of the BIK elements, then PI can be represented in a compact form given in this form, which in matrix form can be written as B0 multiplied by theta 0 vector should be equal to P0 vector, where theta 0 and P0 are the corresponding unknown phase angles, known or unknown phase angles, and the known real power injections in terms of generations and demands. For PQ buses, definitely there won't be generator connected to it, so PGI is 0. For other generator buses, PGI may be given, may not be given, it could be 0 PU or any other non-zero value. Now, if you focus on B0 matrix, so basically this entire equation, it represents the DC model of the power network. B0 matrix is always a rank deficient matrix. For an n bus network, its rank is always n minus 1. Why is that? Please refer to the example that we discussed in the last discussion on fast decoupled power flow, where we were trying to evaluate B dash matrix from the imaginary component of Y bus dash matrix. with indexes running from 2 to n, 2 to n, assuming bus 1 is slack bus. Y bus dash, if we evaluate, which considers only phase shifters and line reactances, then the imaginary component is also having no actual information with respect to connection to ground, which is essentially the case that connection to ground is lost and unique bus voltages should not be obtained, although there are ways of how we can obtain them, but all bus voltages or all buses or nodes, they are floating with respect to ground, which is where Y bus dash, the way we evaluated for the last example or the example that we chose for Newton-Raphson power flow for voltages in polar coordinates, the Y buses were singular matrices, their inverses were not possible. And that is the reason why B dash also, if it is to be obtained in the just as the imaginary part of Y bus, that also will be an inverse sort of a singular matrix. The same analogy is true for B0. The way B0 is evaluated, if we see the term here, then off-diagonal terms are negative of the corresponding line reactance inverse, whereas the diagonal terms are sum of all inverse line reactances which are connected to bus I. So, if I take the addition of all elements of the ith row or the ith column, it is very well observed or can be sort of deducted from the fact that if this is BII and here I have, let us say, K, BKI, then all of the BKIs, their addition would try to cancel the corresponding diagonal term, which is what is the reason why B0 is a rank deficient matrix. For an n bus network, it is rank is always n minus 1. So, if its rank is always n minus 1, that means this equation cannot be solved. That means theta zeros cannot be obtained for known P zeros. And that is the reason why we have to choose one of the bus as bus 1 is chosen as the angle reference bus, so that one of the voltage phase angles becomes known and then the other voltage phase angles can be uniquely obtained for other known injections. So, that is the reason why in DC power flow model, this equation gets converted into a form of B dash, theta and P, where theta is all voltage phase angles for buses from 2 to n, with the assumption that bus 1 is angle reference bus. And since bus 1 does not require theta information because its value is already known to be 0 radian for the sake of convenience, we do not require P1 in this vector because P1 is playing no role because phase angle of bus 1 is already known. So, B dash matrix is essentially B0 matrix, but one row and column removed, specifically the reference bus row and column removed. So, B dash here is a n minus 1 cross n minus 1 matrix, whereas B0 is a n cross n matrix. There is a reason why I have mentioned B dash here. If we evaluate B dash the way it has been explained, it is precisely the same B dash matrix that we see in the P theta half iteration of fast decoupled method. Once B dash is known for known real power injections, B dash is now a full matrix, its inverse is possible. We denote that inverse to be X, and once we know real power injections at every bus except for bus number 1, we can then find all phase angles which pertain to these phase angles. Since this is a one-step equation, DC model is a linear model, it is a linear technique, there are no iterations or recursions involved, there is no need of initial choice. It is a purely reactive model. Since there are no line resistances considered, at the end if you try to find the real power loss through absolute line flows, they will all be zeros because line resistance has never been considered at all. After obtaining all voltage phase angles, we can apply the same assumptions on real power flow for a line between bus I and K. GIK is neglected, its presence is not required. The sign term is replaced by the corresponding phase angle difference itself. Voltage magnitudes are both 1, and so PIK is absolute voltage phase angle difference with inverse of the line reactance. So, this is the final expression of real power flow in terms of voltage phase angle difference. Having obtained these phase angles, we can use the above expression to find real power flows, and which is where the quick assessment of network impact or impact on network for a given outage in terms of contingency, line outage, generator outage, increase in load, decrease in load, generation change can be easily obtained in a one-step time efficient manner, and that helps the network operators. So, DC power flow, it provides reliable bus voltage phase angles for nominally loaded high voltage transmission networks. We will see that efficacy of DC power flow with respect to this statement through this example. The network data is different from the network that we have considered earlier. Since there is no necessity of PV and PQ buses information, and hence I have chosen both bus 3 and bus 2 to be PQ buses, although bus 3 could have been a PV bus also. Bus 1 is the angle reference bus. There is no necessity of the slack bus here, it is just an angle reference bus with voltage magnitude specified as 1 per unit. The demands at bus 2, specifically real power demand, because reactive power demand also does not play any role in DC power flow, because all buses are assumed to have infinite reactive power capacity. So, if at all there is a reactive load present at bus number 2, it will get satisfied through its own reactive power infinite capacity that it has. And that is why PD2 and PD3 are mentioned in DC model for two operating conditions, one for the light load condition, the other for the heavily loaded condition, where the load has now become 5 times of the light load condition. We will try to solve DC power flow for both these conditions given this power network and compare its solution with the AC model of the power network. So, what I have shown first here is that I have obtained the AC power flow solution for this network considering this load model. I have not chosen any reactive power demand while I was trying to solve AC power flow. The AC power flow has been solved using Newton-Raphson technique. There are no reactive power loads. So, all PQ buses that I have here, I have chosen their Qs to be 0 to find. So, Q3 is 0, Q2 is 0 for AC power flow, the solution of which I have shown, one for the light load condition and the other for the heavy load condition. And since I am focused or bothered more about the real power flows, the corresponding real power flows on the lines have also been obtained. So, if I were to just correlate these numbers, so P12 AC means the flow of power from bus 1 to bus 2 just after bus 1. So, this is equal to 0.457158, and similarly bus 1 to bus 3 is 0.41284. So, I have a flow of 0.142842 from this end, and the next flow is from 2 to 3, which is 0.057158. Since the lines do not have their resistances, the forward flows and reverse flows, they match each other in terms of quantum, the difference of sign only comes in. Now, if I were to see that does this power flow satisfy the loads? So, for the light load condition, the load at bus 3 is 0.2, load at bus 2 is 0.4 pu. If I superimpose the same flow of 0.457158, which is coming from this end, then 0.4 is the load, remaining power is flowing to line bus number 3 from line 1, 2, and together these two numbers match up with 0.2. So, my flows are consistent. Similarly, I have also shown the flows for the heavy loaded condition. This also you can check whether these numbers match with the loading conditions given over here. So, having obtained this Newton-Raphson power flow, AC power flow solution for 0 reactive powers at bus 2 and bus 3 with bus 1 acting as the slack bus or the angle reference bus, the next part is to solve the DC model, DC power flow. So for DC power flow, we find the bus admittance matrix. Since the network itself only has reactances, there is no need to ignore any other element. There are no other elements present at all in this network. So Y bus is JB. We take out B0 with minus B. B0, as you can see, is a rank deficient matrix. Bus 1 is the angle reference bus. So we extract B dash from B0 as B0 is 2, 2, 3 and 2, 2, 3, which is this submatrix element. The injections at bus 2 and bus 3, they are negative of the load injections. So for light load condition, these are minus 0.4 and minus 0.2 pu. We put in these numbers here, we get the corresponding voltage phase angles in terms of respective radians, and from using the real power flow expression equation from DC model, we now try to evaluate the DC power flow, which if we now see the numbers that we have obtained in terms of real power flows for the DC model, they match very closely with the numbers that we have obtained for the from the AC model. And that is where the beauty or uniqueness of DC model comes in for light load condition. For the heavy load condition, if we do the same exercise and find the DC power flow, the numbers that you see here for the heavy load condition, where the load at bus 2 and bus 3 are 2 pu and 1 pu respectively, the numbers that are shown over here, the flows, they are different from, or they have differences from the corresponding AC power flows, which is where the fact comes is that the accuracy of DC power flow goes down as the loading of the system increases. So that's all for the DC power flow model. It's a very simple technique, linear, non-iterative technique, has good, in fact, it has always perfect convergence as long as B dash is not a rank deficient matrix. And it helps the system operators assess, get a good assessment or a quick assessment of what would be the impact on the network if at all the network experiences changes. Those changes are to be seen from the perspective of real power flows and voltage phase angles. The next discussion would be the last discussion on power flow analysis module, where we would understand a dedicated power flow technique specifically for radial, weakly meshed, low R by X ratio, high R by X ratio networks, which are the distribution networks. The conventional Newton-Raphson technique, Gauss-Seidel technique, they don't work well for a very low voltage, highly radial, high R by X networks, because the Jacobian elements in Newton-Raphson tend to become ill-conditioned. The Jacobian matrix tends to become ill-conditioned because the corresponding Y bus tends to become diagonally off dominant, and that's the reason why one has to also understand or learn a technique specifically for distribution network power flow analysis. With that, I conclude the discussion. Look forward to more discussion on distribution power flow technique the next time. Thank you.